So welcome to this pre-recording of lecture 9 of a course in supercomputing. So today we will define a parallel summation algorithm with the fanning out of an array. So the fanning out will be taking a logarithmic amount of steps in the number of processors. So we outlined this idea of the fan out earlier lecture, but we really didn't define it very precisely as an algorithm. Algorithm in this course is essentially with code. So I will show the fan out algorithm twice, once in C and once in Python. So in and around, so the parallel summation is one of the main topics. I will first define how one can arrive at strategies to make programs run in parallel. Data partitioning is one of them. So the parallel summation itself is not so exciting, but there is the application of computing the expansion of pi, the hexadecimal expansion of pi. Then the summation there, one can use multi-precision arithmetic, and one does that indeed, but with a special formula one can actually compute the hexadecimal expansion, then it becomes a string concatenation. So this lecture is somehow also closing off our first introduction into message passing. We have already seen many useful instructions. So last time we ended the probe, which was an immediate when we did the load balancing. Here I will give examples. I will define what is the immediate send and receive. So two more examples of non-blocking point-to-point communications. And for the fan-out algorithm, there is actually a synchronization step that is needed. So that's another good illustration of the barrier. Okay, when we want to think of making parallel programs, there are two main techniques. So one can think of the functions one executes, or one can be data oriented. One can distribute and decompose the functions. So we have seen Monte Carlo simulations. One runs a large number of random samples, and one does something with these random samples. So what one does with the samples gets distributed among several processors. So in a functional decomposition, we distribute the arithmetical operations. In a domain decomposition, we distribute data among several processors. One example that we have covered already is the computation of the Mandelbrot set. So we want to compute a picture, and we distribute the picture among the processors. When one solves parallel computers, and here is an application, if you want to, many games are becoming, in some sense, very boring if one considers the game tree. Perhaps not boring if you are from the point of view from a programmer and you want to build your opponent, so the computer, into a very interesting partner for the games. Then these large game trees, they actually are distributed. So that's one example of advantage for using parallel computers, because one has much more memory. Okay, so divide and conquer methods, they are very good problem-solving techniques. They are used in sorting, so merge sort and also quick sort can be considered as examples of this. And one can see this as another illustration of the data partitioning, how one constructs parallel algorithms for sorting. So we will come back to that later. But sorting, applying merge sort, so one divides the data equally among the processors sort, and then when the processors send back to the manager node, then does the merging of the numbers. Okay, let us consider the parallel summation algorithm, which is an example of also divide and conquer. So if one looks at the summation of these 8 numbers, one could see this as a very strictly sequential process of doing 7 additions. But if you look at the partitioning, so you look at the sum in a recursive manner, then the tree structure, so in computer science we draw trees normally from the top to the bottom, but here we have the tree nicely with the leaves at the top. So the leaves are the numbers that we sum, and the inner nodes are the operations. So this is an example of what one calls the prefix sum. So we will encounter that algorithm later. Summation in its own might not be so attractive, but numerical integration is a widely used operation. And instead of at the leaves, compute just we have here these numbers given, but it could be that we have to call a complicated function on every of those numbers. So instead of now doing this in 7 steps, if we have to take the sum with the 7 additions, we can do this in 3 steps. So the divide and conquer reorganization creates parallelism and also results in an algorithm that is faster, and it's also more accurate. So as a numerical analysis, one can show that the amount of round off is actually reduced in this way. So this is also a benefit of doing the summation in this manner. Okay, typically we have more than 8 numbers to sum, but here is an example how you can chunk a very huge sequence, so n numbers, how one can distribute them among the processors. And here is where the scatter comes in. We have this array, this very big array of numbers, and they are scattered. So the scatter operation is an operation provided and defined in the message passing interface. Here in this lecture, we will define the message passing via point-to-point communication. We will very explicitly define these scatter in a fan-out. So, and this is a communication pattern that follows this divide and conquer. So it fits in the strategy, in one of the strategies to introduce parallelism. So I will spend most of the time on the fanning in, on the fanning out. The fanning in is then the mirror operation and is actually left as an exercise. If you understand the fan out, then you can also do the fan in. Okay, so we have these sums that we will distribute. And this is a hands-on course. I will illustrate this with an array of 80 numbers. But here is the algorithm. So the algorithm is shown with a picture. So all data is at the manager node. In a sequential scatter, uh, the root node does first sends first the subarray to 1, then to 2, then to 3, and this will take 7 steps for the manager to send all the data to all the workers. The idea of fan out scatter is that half of the data, the second half of the data, first gets sent to worker 1 or to node with ID 1. So you can see this at the right here. In step 0, so we start here to count from 0, so we have our 8 parts, the 8 numbers. So in step 1, what happens is that the data starting from index 4 up to 7, half of the data gets sent to node 1. In step 2, the node 0 repeats the same procedure, sends now the second half of the first 4 numbers to node 2. So we see that after that step, node 2 has the data going from 2 to 3. And also node 1 sends to node 3. This essentially do the same operation. And there's one more step. So here on my slides, I'm a little bit limited to what I can show. But if you understand the 3 steps, then you can understand the entire algorithm. So here this algorithm is defined by the nodes. So which node send to which other node. So for every send there is a matching receive. For every receive there is a matching send. So this is why in this loop here, so you see that the process IDs J, the sender becomes then the receiver. So the sender, the source, becomes the source, also is also the source in the receive operation, and the destination is actually the processor that executes the receive. So the data gets each time divided in smaller and smaller pieces. So this is a case where the level, the depth k of this tree, so there's also a tree structure here, so you can see the tree in the data. So this algorithm is a little bit more precise in the sense that the data is actually indexed. So you see that node 0 at the end has the data, the first block data, or actually the first number if we only scatter 8 numbers. The last node has the last data. But you see that there is some reshuffling that happened. But in the summation we can do this, so there is no strict order here. So I should say that instead of the summation, we can take the minimum or the maximum. So, or we can do the product. So this works with any binary arithmetical operation. Okay, so let's try to program this. And first we actually need to look at the binary expansion. So there is the bit patterns in the nodes and in the data locations. So we have the indices of the nodes, and then we have the indices of the data. So, and you can see that with this fanning out, that's another check. So where does the data end up? It's the opposite. So the bits in the identification number get shifted, gets just flipped. in the binary expansion. Okay. Um, Here is a run out of the program. This is a program where it is in lockstep. So there we are fanning out 80 numbers. So at the end, every processor will have 10 numbers out of an array of 80. So this runs with 8 nodes. So you see the output, the first cent is half of the array, and then it keeps on going like this. So we have the stages. We have 3 stages, the 2 logarithm of 8, and we have the depths or these are the portions. So this is what we use for determining the sizes at each step. Okay, so then at the very end, we have the first numbers that are at the identification, the processor with identification 0, and the last numbers are at the last node because the bits sequences are the same, but then you see the flip that happens with the bits. Okay, this is a synchronized. Synchronization is very good to have the messages sent, but everything needs to happen in lockstep. So for the correctness of this algorithm, we must apply the MPI barrier. So what barrier does, so this is in the single program that's executed. So we have one same program that's executed by all processors. So we will define in the later states when we get to synchronized algorithm, we will define algorithms that say that there is a trapping stage and then there is a release stage. So every processor has to have executed the statements that come with the MPI barrier. So this is a blocking operation. Okay, so this is a technical function here. So it's defined in C. So this is, if you like, to think of it in a mathematical sense, it's kind of a lemma, a helper to compute the beginning of every portion that gets sent. And that is sent based on the data of the size. And based on, so every node, we can compute what is the offset in the data what gets sent. So there is not really an algorithm for this, but there is the function that gets computed. So we have the repeated division. So we divide the size by 2, and each time, as long as we are not at 0 with the remainder, we actually add to the offset. So this is not a formula, but this is an algorithm, and the algorithm runs very fast because it's also repeated division, and there's logarithmic in the label in the input n. Okay, so then the MPI program first defined in C. So there is the initialization. So note that there is this capital A. The capital A is the entire array of 80 integers long here. every processor has the same array, doesn't have the same array, but has essentially space for this array. So for these 80 numbers, even though only the manager has the entire data. So the manager at the bottom here assigns, so we have the consecutive integers starting from 0. So every MPI program starts with an initialization where we get the number of processors and where we also get the identification number. So in a way, this is the self-contained introduction to message passing. Every processor executes the same program, and we discriminate which instructions are executed by what processor, and that is done by these if statements. So we distinguish by this if my ID is whatever. In the manager worker paradigm, it's typically test on 0 or positive. Okay, so here is where the parity offset is being used. So this computes the beginning. And this is essentially an interactive program, but I doubt whether it actually would work with the verbose off. So actually the MPI barrier should actually be there also if the verbose is set to 0. So because there is this synchronized stepwise, so here we have 3 levels starting from 0, 1 and 2, because 3 is the 2 logarithm of 8. So each time we double that d variable. So note that the offset is computed based on the processor ID. So the processor ID will calculate where to send. And the size will be each time divided by 2. Okay, so then we have the send and the receives. So in some sense, the printout statements can be seen as some kind of a documentation. But here you see for every send, there is a matching receive. So my ID equals to j, sends to j plus d. So in the send, so my ID equals to j, the destination is j plus d, and the corresponding identification, this corresponding processor with identification number j plus d does the matching receive from the source j. So it's not anymore a trivial algorithm, but verifying the correctness. For every matching send, there is a matching receive. For every receive, there is a matching send, can be done. So you also see here the offsets, how the sending happens. So the offsets that are computed in the source and the destination. So the size of the number, the little s, gets each time divided by 2. And in the C version of MPI, we give the beginning address, the start address in that array. So it would be possible to be a little bit more frugal with the memory, but that would be because actually at the end, it depends on how far the root, so the higher processors, the higher workers, which mean the workers with the larger identification numbers, they actually don't need the entire array. But that would have made for a more complicated implementation. Okay, so the algorithm is in the end not that bad. So at the end, there is a barrier, so where the manager node actually prints that message, but then every node prints the beginning 3 numbers of what they have. Okay, so that was the algorithm defined in a program, in a working C program. Let's now redo this with Python and MPI for Pi. So in some sense, this will go faster. I will not show the parity function, which can be very easily translated into Python. I will mainly show the main program. So we have the getting, so every process gets its identification number. So the initialization happens all the way on top. It's natural to use arrays. So we could have used, if you do not have NumPy installed, Python also has an array type. We can also use that. But here, let's use NumPy because MPI and NumPy, they work well together. So it's important to allocate. So every worker must allocate space for, so that's the mirror statement from the big A in the C program. Okay, and then Python is a lot faster. So here I removed the barrier statements. I also removed the verbose statements. So in some sense, this is the website will contain everything. So the program that I post at the course website has the complete program. But here the algorithm is quite nicely defined. You see again the sending and the receive operations. It's very nicely symmetrical with the source and the destination. So the source, when the source is j, then the destination is j plus d. If the source of the receiver, so if the receiver j plus d receives a message, then the source equals j. The slicing is also quite nicely done with NumPy. So we slice, from the data, we select the data that we are sending. And also when we actually slice, it's getting a reference. So in the receive operation, when we do the slicing, we actually pass the reference to the receive operation. So MPI for Pi is case sensitive. We use the uppercase send and receive that allow us to provide the data. So each time the size gets divided by 2, so this is Python 3, so this is the integer division, and we double each time the letter D. And the D, now I should have explained this earlier, that is actually the distance between the sender and the receiver. So that's a drawback from choosing very small letters names. So it's actually not really the depth, it's the distance between the identification numbers. Okay, so that is the parallel summation. In some sense, this is the essence of the lecture. For completeness, I give the mirror. So this is the fanning in of the results. So the program would now continue. So in the example, we had 80 numbers that get scattered. Every processor has 10 numbers, does the sum of these 10 numbers, and then the sums need to be gathered to the root node. And this can be done also in a logarithmic number of steps. Logarithmic because of this fanning in algorithm, which is here shown. So it's an exercise to adjust the code so that you can do the fanning in. All right, here I will just mention a nice application. So the computers, the supercomputers, one benchmark problem is to compute the decimal expansions of pi. Um, there is this algorithm, PSLQ algorithm, that discovered a relationship in the hexadecimal expansion of pi. And this allows to calculate the hexadecimal expansion without having to compute all the previous digits. And with the addition, I said that you could, in some sense, work with strings. If you look at the hexadecimal expansion in the string representation, then the plus would be the concatenation of the strings. Here are the references. So this PSLQ algorithm is defined in the first. You can find the result, the Spigot formula for pi in the second reference. And then there is the work that's done, one recent, well, it's not so recent benchmark anymore. I didn't check what the current record is, but you can see in 2010 how many 2000 billion of numbers. So these are trillions of decimal digits that can be computed on a parallel computing with multi-precision arithmetic. Okay, so for completeness, and I'm actually going a little bit fast through this lecture, perhaps. This is so this lecture is kind of concluding the segment on message passing. We will see more ingredients of programming distributed memory computers in this course. But starting with lecture 5, we have seen already very useful MPI commands. So to make the distinction between blocking communications. Blocking communications is what we have used so far, the MPI send and the MPI receive. So this requires a synchronization. So in some sense, we will use this to implement barriers later on. This is desirable. But if you want to write more efficient computation, so in the blocking, the sender must wait till the message is received and the receiver is blocked until the message is sent. So this is kind of a rendezvous between two processors. But if you want to overlap communication with computation, if you can already continue without having to wait. So if, say, the partial results, if worker nodes send their results and they don't have to wait to continue, then they can use the immediate send. And there is also the immediate receive. In a way, this it can be much more efficient if you have a very substantial communication overhead. So if there is a large communication overhead, then it's still not hopeless. Then you can use the immediate send and the immediate receive. They are in some sense easier to use. So sometimes when your parallel program seems to get stuck, it might be tempting to switch to the immediate send and the immediate receive. But they are actually some sense more harder to use because you have to test on the status. And eventually you can also have a hybrid. So if a worker node can still continue the computation, but then at some point gets stuck because there is no more data coming in, input jobs, then it can be put into a waiting mode. So you can actually wait on the status. Okay, I have no examples on how these things are used, how these commands are used, but I think it should be fairly straightforward. It's the same syntax as the send, except that now, for the send, there's actually not really anything that changes, except the last two sentences on the slide here. This is in C syntax. You actually pass the address of the buffer, so you pass a reference in the more general. So if in the meantime the buffer would change, then this would change the outcome of the send. So the send is executed at some point whenever the recipient is ready. So that's the destination, the rank of the destination. Whenever that processor is executing the receive, then the send is being done. So there is already a warning here, so there can be a lot of side effects. Then in the receive specification, so there is this the same comment. So the first argument is the location of the data, and that should not change until the statement has been completed. Okay, so with the iProbe, we have seen that there can be any source. So it is possible to query for. So this could be very useful if you want to break the manager worker paradigm. So with the manager worker paradigm, there is a very strict protocol and hierarchy. If you are implementing more a work crew, you have several processors who are each more autonomous, they can send to every other processor, then the immediate receive and the immediate resend could be very useful. Okay, then there are the query operations. So there is a request that is each time the last argument. One can check the status of the request. One can wait until the so in that sense, one can turn an immediate operation into a blocking operation. Or we can also test on this. So there can be a specific busy wait loop that is implemented. Okay, so I'm at the end, so in about a little less than 40 minutes. So there are some exercises that are suggested. So in my implementation, I was restricted to 8 nodes, and that should work also on a laptop. But you may want to modify this. So we have now access to a supercomputer. And these are already interesting programs to test the communication overhead. So running this fan out algorithm for 8 nodes, you should perhaps see some improvement over the sequential scattering, but it might be very interesting to compare the fan out, so let's say for 64 or 128 nodes, with the point-to-point communication, where the manager is going to in a loop send to all the worker nodes. So this will take 127 steps. If you do this in a sequential scatter, or also sequential broadcast if you send one number, but it will happen in 7 steps, and that's quite a significant order of difference if you do this in the fan out. So we have the fanning in. So I did not give that algorithm. I did not. I just sketched it, but I did not define it with code. And this code would be necessary if you really wanted to do the summation in this way with the divide and conquer. Okay, I hope this lecture was interesting. I thank you for watching. This is lecture 9. In lecture 10, we will start with shared memory parallel programming. Start with the introduction of OpenMP.